Hey, everyone. Welcome back to the channel. Today, we're diving into a fascinating TOK Title 5. To what extent do you agree with the claim, all models are wrong, but some are useful, attributed to George Box? In the realm of science, models are essential tools used to simplify, explain, and predict complex phenomena. George Box's famous assertion that all models are wrong, but some are useful, emphasizes the inherent limitations of models while acknowledging their practical value. Although models are never perfect representations of reality, they enable scientists to conceptualize and investigate the natural world. This notion is evident across various disciplines, from physics to biology, where simplified models play an indispensable role in advancing knowledge. In physics, the kinematic equations serve as a useful yet simplified model for describing the motion of objects under uniform acceleration. These equations assume that objects can be treated as point masses, disregarding factors such as their shape and mass distribution. Though this assumption may seem overly simplistic, the model remains a powerful tool for solving a wide range of problems in classical mechanics. When forces become more complex and acceleration is no longer uniform, Newton's second law of motion steps in to refine the model, linking force, acceleration, and momentum. Thus, while the kinematic model is incomplete, it is a valuable stepping stone that aids understanding and serves specific practical purposes. The same principle holds in thermodynamics, where the behavior of gases is often modeled using the ideal gas law. The ideal gas model assumes that gas particles have no volume and that their interactions are perfectly elastic, assumptions that are not fully accurate in the real world. Nonetheless, the model provides useful predictions about pressure, volume, and temperature, allowing scientists to explore the macroscopic behavior of gases based on the motion of individual particles. An ideal gas always obeys the gas laws. In fact, no real gas is ideal at high pressures and high temperatures. When the pressure is roughly atmospheric, the approximation to ideal behavior is good. By linking bulk properties to microscopic behavior, this model enhances our understanding, despite its limitations. Theoretical models are based on a set of assumptions about the system they model. Theoretical models are, superficially, very attractive because they appear to allow predictions for all circumstances. But this is an illusion. Even today, attempts to produce a unified theory for all gases under all conditions have not been successful. An important piece of work by the Dutch scientist Johannes van der Waals, mentioned later in this topic, requires individual sets of empirical constants for each individual gas for his theory to work. We still need empirical results when the assumptions of a model break down. Quantum mechanics dictates that we can no longer model the hydrogen atom as a system of an orbital electron and a stationary proton. Nor can we use the Bohr model to explain photoelectricity. Bohr himself knew that his model was limited to the simplest atoms with one electron. In the photoelectric effect, the incoming quanta are interacting with free electrons near the surface of a metal. The bonding between electron and metal cannot be modeled using Bohr's ideas. All physical models have limitations. It is the role of the scientist to appreciate these limitations and either work within them or strive to improve the scope of the model. In biology, models are also invaluable for explaining phenomena such as enzyme activity. Two well-known models, the lock and key model, introduced by Emil Fischer in 1890, and the induced fit model, proposed by Daniel Koshland in 1959, attempt to describe how enzymes and substrates interact. While the induced fit model has gained widespread support due to its predictive success and experimental confirmation through high-resolution X-ray analysis, the older lock and key model has not been entirely superseded. This persistence highlights the utility of even imperfect models in specific contexts. The lock and key model's simplicity and clarity make it a useful teaching tool, and it remains valid for certain enzymes. Koshland's induced fit model, though more accurate in many cases, is still considered a model, and like all models, it is subject to further refinement as more evidence becomes available. Both models, despite their limitations, continue to be useful in advancing our understanding of enzyme activity. The persistence of the lock and key model alongside the more accurate induced fit model demonstrates that models are attained as long as they offer utility in specific contexts, even if they are not entirely correct. Similarly, physicists often switch reference frames to make phenomena more accessible. For example, in a rotating reference frame, the introduction of fictitious forces explains why a coffee cup slides inside a turning car, even though these forces do not exist in an inertial frame. This shift in perspective shows the adaptability of models in physics to suit different explanatory needs. In conclusion, the claim that all models are wrong, but some are useful, captures the essence of how science progresses. While models are simplified and imperfect representations of reality, their power lies in their ability to guide experimentation, generate predictions, and refine our understanding of complex systems. Whether in physics, biology, or other scientific fields, models help bridge the gap between theoretical knowledge and practical observation. As our understanding deepens, these models evolve, but their usefulness remains at the core of scientific inquiry. Thanks for tuning in. If you enjoyed this video, don't forget to like, subscribe, and let me know in the comments. What's your favorite example of a useful model?
See you next time.